Okay, hello, welcome to the first session, fault attack models and countermeasures. The first talk will be given by Roukoz Nabhan from Mines Saint-Étienne, and the title is A Tale of Two Models, discussing the timing and sampling EM fault injections models. Okay.
Thank you. Thank you for your introduction. Hello, everyone. My name is Roukoz Nabhan. I am a PhD student at Mines Saint-Étienne. My thesis is supervised by Jean-Max Dutet and Jean-Baptiste Tricot from Mines Saint-Étienne side, and Jean-Luc Danger, Laurent Sauvage from Telecom Paris side. The subject of my talk is a tale of two models discussing the timing and sampling electromagnetic fault injection models. Securing integrated circuit against fault injection attacks is an ongoing challenge. To develop effective on-chip detection sensors as countermeasures against electromagnetic fault injection attacks, it's crucial to study the mechanism involved in injecting fault due to the EM disturbance. So the objective of our paper is to test the effectiveness of a fully digital detector designed by an LBAS AI embedded in AES accelerator. And we tested its functionality across a full frequency range of the FPGA car. I divide my presentation into several parts. I will start with an overview of EMFI model exists in the state of the art. After that, I will pass to describe the architecture of the fully digital detector chosen. Then, in the second part, I detail the experimental setup, precisely the EMFI platform and device intertest block diagram targeted test vehicle. After that, I underscored the experimental result, the EMFI result reported, and underscored a deep exploration of EMFI mechanism and the analysis of this EMFI result. After that, I go in-depth analysis and examination of EMFI-induced clock glitches, and in conclusion, to sum up our research findings. Previous publication explained EMFI models through sampling fault models by observing the effect of EM disturbance on the D flip-flops sampling operation. This fault is occurred around a clock rising edge within a susceptibility windows, where the probability of injected fault is maximum inside these windows and is limited elsewhere. The width of these windows is constant and independent of clock frequency, and at fault logic model, it's bit set or bit reset dependent on the polarity of the pulse. All these characteristics are based on experimental result and modeling of EMFI effect on the power distribution network of an integrated circuit. And we say in the state of the art, we see, and in contrast to the sampling fault model, timing violation fault model with two different mechanisms, where the Habawi EL present timing faults due to the EM disturbance coupling with the target power distribution network, when a transient decrease of the supply voltage increasing the critical path, surpassing the clock period, and a fault is included. And this timing violation, it's a bit flip at logic model. And also in the state of the art, we can find EMFI-induced clock glitches by Godrati al, with the EM disturbance coupling with the target clock distribution network, induced clock glitches, which shortening the clock period and a timing violation obtained and a fault is induced. And it's as well as timing faults, it's a bit flip. After showing an overview of a mechanism which shows a fully digital detector designed by David Elbaz, which is by design, it's based on the sampling fault model. This detector is constituted of two DF flip-flops, FF1 and FF3, which is initialized the first one at 0 and initialized at 1 for the second, to monitor both transition 0 to 1 or 1 to 0. Okay, these two DF flops give two detection windows. In objective, to increasing to increasing the fault detection windows, two deflops are added, TFF2 and TFF4, but it's toggling in the 180 phase shifted clock signal. It's clock 180. So how does this detector work? From an initial state, 0110, which is 4 outputs of this 4 flip-flops, stayed in is a closed pathway under normal behavior, for sure. Under attack, it deviates from this closed loop, and alarm will be raised anytime we have an attack. Now we start to detail the experimental setup. By AMFI platform, we use an FPGA target. It's a Nexus Video 7, which embedded an RTX 7200G. And we need AVTech voltage pulse generator, which pulse amplitude, it's up to plus minus 750 volts. Okay. So our objective is to test the efficiency of the sensors, as well as to study the mechanism of AMFI. That's why our design and test, it's an AES plus sensor, which this sensor is embedded inside the block as calculated. In addition to this block, we have a serial communication block to communicate data, plain text, and ciphertext in between. Okay. In addition to that, we use a clock generator block. It's given by an FPGA in Vivado, which is generating several clocks, clock 0 and clock 180. Okay, toggling the sensors and the AES block. No, this schematic shows the floor plan of our device under test extracted from Vivado tool. Okay, we put the clock generator far enough under localization constraint, far enough of our target location. A close-up of our target location, we see the distribution of our 16 sensors in a yellow rectangle, with this sensor is locally distributed inside the AES block. Now, when we do a full cartography, when we get a sensor sensitivity map for all the spaceship of the FPGA card, we obtain 2 areas. Okay, a top one and a bottom one. The bottom one is corresponding with the clock generator block, as this all 16 sensors are triggered at the same time. And the top area defines the target location position. So what is the methodology of our campaigns? We fixed our electromagnetic injection probe above the accelerator sensitive area. Why we fix it? Because our objective is to study the ability of this sensor all over the target's full frequency range. What happens if this target is at 100 megahertz? It's pulse amplitude plus 420 volts. In the gray curve, we see a consecutive detection windows where these sensors, one of the 16 sensors are triggered. And the blue and the green line is faulted bits and bytes injected in the AES calculation block. We see that we obtained a consecutive injection windows corresponding with the AES rounds calculation, with a periodic injection windows obtained, okay, where it's consistent with this mechanism of the sampling fault model, where the corresponding between detection windows and injection windows, it's precise the position of the clock rising edge, and the next one is corresponding to the clock falling edge, which respect what is mentioned on the state of the art of this sensor. Okay, for alarm failure, we see that all the injected fault in the AES are detected by this sensor. No alarm failure, all injected fault are detected. We find the same behavior for all frequency until 200 megahertz. What happened at this frequency? This frequency is close to the device under test maximum clock frequency. We see is a different behavior obtained. Okay. No more periodicity injection windows in the AES. Okay. And we see that a bad detection for this sensor at high clock frequency. That's why we put an hypothesis. It's timing fault model in addition to sampling fault model. But we see at this frequency, the threshold voltage amplitude required to inject fault in the AES, it's 400. But if we decrease until 350 volt, we see none of this alarm are triggered. Okay, but we injected fault in the AES. Okay, This behavior at this frequency for a pulse's amplitude at 350 volts, it's the timing fault model induced, and it's no sampling fault. So to get a deep exploration of EMFI mechanism, obtain all the target full frequency range, we draw in x-axis the frequency range from 10 megahertz until 200 megahertz. And in y-axis, it's the pulse amplitude, it's the threshold voltage amplitude to inject fault or in AS or to trigger sensor onto different electromagnetic injection time. If I start the position 1, it's when detection windows to trigger sensor. We see that it's 380 volt, the threshold voltage amplitude required to trigger sensor, okay, for all frequency range. But for inject fault into the IS calculation, we see that it's constant 380 volt until 150 megahertz, which is decreased progressively until 290 volt at 200 megahertz. When the orange line is below the blue one, sensor failed. But if we take the third electromagnetic injection time, where the time it's between these two detection windows, okay, we draw a third line, it's in green, where at 120 megahertz, the threshold voltage amplitude it's 720 volts, okay, and it decreases progressively until 320 at 200 megahertz. This line reflects the timing fault as well as the slacks to get evaluation time. So this three curves shows the coexistence of two distinct fault injection models mechanism at the same time to explain EMFI. That's why I invite you to my publication in date 2023 for more details. If we get a closer and more details in the characteristic of our experimental result, specifically, if we study the width of our detection windows, we see a lot of discrepancies with the sampling fault model in the state-of-the-art defined. We see that the width of our detection windows decrease when the clock frequency increase, which is in contrast with what is mentioned for the characteristic of the sampling fault model, as well as our experimental result depend on the input data and is reduced when shortening propagation delay path. It's in contrast what happened for the characteristic of the sampling fault model. As well as at fault logic model, we see that we obtain a bit flip. It's mix of bit set and bit reset. No depend of the pulse polarity, but it's in the state of the art, it should be bit set or bit reset. So the fault injected at low frequency broadly follows the sampling fault model, but it's not. It's some discrepancies from the theory cast doubt on its validity. So further exploration and tests are needed to reconcile theory and practice. So what is the mechanism of fault injected at low frequency and low and moderate frequency? In this schematic, we see a screenshot from an oscilloscope where we outputted a trigger. We calling it AS on. What is the signal? It's signal passed to 1 during the AS calculation block from init until store with the 10 rounds for do a complete AS calculation. Okay, and a clock signal at 10 megahertz. Okay, the width of this AS on, it should be corresponding to 12 clock period. The width is 1200 nanoseconds. And now we study the effect of EMFI effect on the width of this AS duration. We see when with a positive pulse plus 420 volt, and when the EM injection time is corresponding with the clock equal to 1, we see that the AS duration is reduced by 100 nanoseconds, what it equal to clock period. And what is good, its ciphertext is correctly received. Meaning of that all the calculation of the IS run are performed. Once the EM injection time corresponding with clock equal to 0, there was no effect. Okay, now how can I explain this behavior obtained in our experimental result? If we take a small animation, we see if we take just the 4 last rounds, R8, R9, R10, and star, we mentioned that EMFI can induce negative glitch. Okay, how can it happen? There 2 rounds under attacks for a same duration for 1 clock period in normal behavior. We do two rounds at the same time. It's R8 and R9. That explain why all the OS calculation are done and performant. And that explain why we reduce the OS duration per 1 clock period. For one AM injection time corresponding with clock equal to 0, there is no effect. To validate this hypothesis, we try it with minus 420 volts to see the behavior. We see that when the AM injection time corresponding with the clock equal to 1, there is no effect. But when is corresponding with clock equal to 0, we reduce by 1 clock period and the ciphertext is correctly received. Okay, how can we explain that? No effect when the clock equal to 1. What we do, we do an EMFI induced positive glitches due with a negative pulse amplitude. To corroborate and to reinforce our hypothesis, we try to trigger 2 EM disturbance when clock equal to 1 with a positive pulse. We see that we have reducing with two disturbance to trigger 2 EM disturbance, we reduce by 2 clock period. Okay, and with ciphertext is correctly received. So we do in fact that EMFI does induce clock glitches in the target clock distribution network, and it can replace genuine clock rising edge. So after I made an evidence that EMFI, EM disturbance coupling with the clock tree can induce clock glitches, now I can show you the principle and the characteristic of this mechanism. 3 distinct behaviors are obtained. When EM injection time corresponding with clock equal to 1, we obtain a negative glitch. Okay, with an EMFI susceptibility windows, it's out of 47 to 48 nanoseconds. When EM injection time, it's with clock equal to 0, there is no effect. But when EM injection time, it's just after the clock rising edge, there we get a small shift of the edges, and it's not an effective glitches. What happened in this behavior? We extended the clock period and we reduced the following one. The width of this susceptibility windows if equal to T over 2 minus 2K, or K is the constant margin when we obtain a small shift of the edges. Okay. As well as by analogy, what happened for positive pulse, it's the same for minus 420 volt. 3 distinct behavior obtained. When EM injection time corresponding with clock equal to 1, there is no effect. When it's corresponding with clock equal to 0, we obtain a positive glitches. And when it's near to the clock rising edge of the clock period, we get a small, just before the clock rising edge, we get a small shift, okay, for a constant margin equal to K. And the width of this susceptibility windows is T over T minus 2K. Now, how this mechanisms explain the experimental result obtained at low and moderate frequency? We divided into 2 parts, one T critical less than T over 2. Okay, as I mentioned before, the maximum clock frequency of our device under test is 200 megahertz. It's around 4.5 nanoseconds. With a clock period 20 nanoseconds or clock frequency 50 megahertz, the T critical less than T over 2. So, with any injection time corresponding with clock equal to 1, as I mentioned before, EMFI induced negative glitches. Okay, we see that these glitches shortening the clock period, and we get a timing violation obtained, and we stopped the calculation for round R8, and we pass to the next round. Okay. But when the AM injection time, okay, we see that EMFI induced negative glitches in the clock, but no effort injected, but because it's obtained after the critical pass. And this explains why the width of our injecting fault depends on the critical path. So we get an corresponding with practical prediction, theoretical prediction and practical observation. What happened when T critical greater than T over 2? And for a clock frequency 170 megahertz. When we get AM injection time corresponding after the clock raising edge, we get only just a small shift of the curve with the edge. This is combination with the EM disturbance coupling with the power distribution network, the critical path is decreased. That's why we obtain a few number of faulted bits. But when the EM injection time is increased, a fault is obtained with the combination of these two mechanisms. The question is, how this detection windows, which is by design corresponding to the sampling fault model, should be effective to the sampling fault model, created to be effective for EMFI-induced clock glitches. Why? Because this sensor is talking with two different separate clock 0 and clock 180. And what is good? When we get a negative glitch on one, no effect on other. That's why it's help this sensor to detect in this block diagram each time we have an alarm. The width of this detection windows is T/2 minus K, which is both accurate and constant with what happened of our inside of our experimental result, which we mentioned that when clock frequency increase, clock period decrease, the width of our detection windows is decreasing. Why all the injected fault at low frequency are all detected? Because for the detection windows, T/2 minus K, you have a width for our injection windows is T critical minus K. We see that all fault injected in AES are detected by the sensor. But we obtain a false alarm where this sensor report in fault in AES, but it's not actually a fault in AES. And in the white one is where is no alarm. So to sum up the AES performance, at low and moderate frequency, when T critical less than T/2, we have a high detection rate. But when increasing the clock frequency, we see that it this performance gradually decrease from moderate to low detection when T critical greater than T/2, as well as no detection obtained in this case. Now, to sum up our EMFI models, we see that when EM disturbance coupling with power distribution network, we obtain timing fault at low slack at high frequency. And when EM disturbance coupling with the clock distribution network, we EMFI-induced clock glitches. We align these two mechanisms under the timing violation fault model. So to sum up, EMFI models, its timing violation fault model obtained in two different mechanisms. When EM disturbance coupling with the power distribution network, it's timing fault. When EM disturbance coupling with the clock distribution network, we induce clock glitches. And for LBAS sensor efficiency, as I mentioned, it's a high detection at low frequency, but moderate at no detection at high frequency. Okay, in this research findings, we highlight the risk of using an EMFI detection sensor based on a single fault model, as well as we present an enhanced explanation of the EMFI models to help designer in developing more effective detection sensors. Thank you for your attention.